Hi, my name is Dimitris Koutsoukas and I'm going to present you Modularis, modular relational analytics over heterogeneous distributed platforms. This is joint work with Inga Müller, Renato Marakin, Anna Klimovic and Gustavo Alonso. Let's start with an overview of the ongoing trends in data processing. On one hand, cloud computing becomes more and more popular as it is easier to leverage well-designed and scalable infrastructure. Also, hardware is evolving very fast, with coprocessors such as GPUs, TPUs and FPGAs becoming more and more popular. Finally, with the boom of machine and deep learning and the abundance of the data that are produced every day on the web, workloads are becoming more and more demanding. It's not uncommon for models to train for days or for queries to run for hours on petabytes of data. All of these factors are influencing data processing. In order to cope with all the recent advances, especially workload and hardware-wise, research and industry build highly specialized monolithic systems that are basically fast and tailored to a specific workload and hardware type. Besides their performance, these systems are very hard to adapt and evolve. When a new type of accelerator or new algorithms are being introduced, these systems have to be redesigned and re-engineered from scratch in order to adapt to these changes. Therefore, we can say that they are designed for optimization and not for evolution. As the current approach clearly is not optimized with the landscape of growth that data analytics experience, a natural research question arises. How can we design data processing systems that easily and quickly adapt to the underlying technology and new applications and deployments? To answer this question, we built a system called Modularis. Modularis is a data management system that is built around small building blocks. The majority of the system is hardware agnostic. Because the system is built around modular building blocks, it's easy to adapt and evolve, and as you will see in our experimental evaluation, it is also highly performant compared to mature systems such as Presto and MemSQL, that is now called SingleStore. The key idea behind Modularis are the building blocks that we call sub-operators. Sub-operators are small composable building blocks. They are more granular than typical relational operators in their majority. For example, a partitioning hash join consists of many sub-operators in Modularis. They are also easily combined and hardware agnostic in their majority. Optimizations are mainly done by restructuring them across plans. The exchange tuples between them and the data exchange is based on the Volcano model. A tuple can be an atomic item or a nested collection of tuples. Sub-operators are divided in 5 major categories. We present the categories and examples of sub-operators in the table above. We have orchestration operators, which are glue operators and responsible for the data flow execution of the programs. Data processing operators that perform relational operations like selections and projections. Materialize and scan operators so that we can read and write to different file formats and we can decouple reading and writing logic from actual data processing. All these are hardware agnostic operators, and to be able to execute workloads in different platforms, we also have hardware consensus operators that are divided in 3 categories. MPI-specific operators, which are responsible for executing workloads in RDMA clusters, Lambda-specific operators, which execute queries in Amazon Lambda, and smart storage-specific operators to leverage smart storage capabilities. In the figure, you can see the general system architecture of Modularis. The user writes a query in a dialect of Python that is similar to PySpark and specifies the platform where the query will run. Then the parser gets the query and transforms it into a directly acyclic graph or DAG of operators that are the data flow representation of the program. Then the query compiler gets the necessary sub-operators and does transformations to the DAG such as projection pushdowns. Next, Modularis cuts the DAG into 3 safe subplans, each of which represents a pipeline with a materialization point at its end. Then, we transform the query into its distributed equivalent based on the specific hardware that the query will run, substituting the hardware agnostic with hardware conscious operators. Finally, the plan is lowered into LLVM-IR and just-in-time compiled to native machine code, and it is deployed to the specific platform that the user has chosen. As it is clear from the previous picture, the query compiler takes the target platform and the query and rewrites it automatically with hardware-specific operators to produce an architecture-dependent executable plan. The current deployments are RDMA clusters, Amazon Lambdas on S3, and Amazon Lambdas on S3 Select. Some of the hardware-specific transformations are having a serverless executor that spawns the workers in a tree-plan fashion, or an MPI executor and an RDMA-based exchange operator. The previous approach has a number of advantages. To add an additional platform, the user has to only write the hardware-specific operators that are needed to run workloads on this specific platform. The system does not have to be redesigned from scratch. Therefore, the implementation effort is reduced vastly, and the underlying architecture where the query runs is another parameter of the system. Now that we have seen the basic principle of how Modularis works and its architecture, let's see how Modularis works in action. I won't go into heavy details, but only present a high-level overview. Interested readers can read the full paper. Here we see a distributed join algorithm as it was proposed by Bartels et al. The different processes get an inner and outer relation part, and they calculate the local histograms and then exchange them to calculate the global histogram. This is needed to calculate the size of the remote memory access window and the positions where each process will read the required data. Afterwards, the processes exchange data through network partitioning. The network partitions are partitioned once again to reduce TLB and cache misses. A hash table is built from the left relation part, and this hash table is probed from the right relation part to calculate the final join result. This is the same plan in Modularis. You see the different processes represented by the stack boxes here. The MPI executor is a specialized operator that spins processes that will run in RDMA clusters. The first three operators on the left are the local histogram, the global histogram, and the network partitioning. And afterwards, you can see in the next boxes the local partitioning phase and the hash build and probe phase. Operators are used across phases, such as the local histogram operator. And as said before, the majority of operators are hardware agnostic, with the exception of the MPI executor, the global histogram here, and the network partitioning. By using the same sub-operators, and only adding an additional sub-operator, the reduced by key one, we can run a distributed group by algorithm. The changes compared to the previous plan, besides the final operation, group by here instead of join, are that we have one relation instead of two. The modularity of the system and the fact that it's based on sub-operators so that rewriting new algorithms does not require rewriting the codebase from scratch, but only adapting the changes required by rewriting the specific sub-operators. And here we see TPC-H Query 12 on two different platforms, RDMA and Serverless. As you can see, the two plans are very similar, and the only difference are the hardware-specific operators, and more specifically the different executors here, and the different exchange phases here and here. After seeing how Modularis works in action, let's now see how the system performs, and more concretely, if modularity comes with a performance trade-off. We present a subset of the experiments run on the paper. We run a representative subset of TPC-H that cover most of the challenges that the benchmark has. For the RDMA backend, we compare Modularis against two different systems, Presto and MemSQL, that is now called SingleStore. MemSQL serves all queries from an in-memory cache. For a fair comparison, we thus exclude the time Modularis needs to read the data from this as well. Modularis is between 30% up to more than 3 times faster for all the queries except query 14 and query 19. For query 19, Modularis is slower because the histogram-based RDMA network exchange is slower than a broadcast operator for small joins. Modularis is 40% slower in query 14 because the map operator does not perform the selective like as fast as SingleStore. For the queries where Modularis is faster, all except queries 1 and 6 have large joins where the RDMA network exchange has better performance. Another operator responsible for a large part of the overall runtime is reduced by key, which uses a highly optimized version of a parallel hash map in Modularis and thus executes very fast, large aggregations. The difference is obvious in queries 1 and 18, where Modularis is 3 and 3 times faster respectively. To compare with Presto and have a fair comparison, we include also the time that Modularis needs to reach the input data from disk. Presto cannot execute queries 3 and 18 and fails because of insufficient resources. Our system is 6 to 9 times faster than Presto depending on the query, partly because of the optimized RDMA network exchange and partly because of the highly performance sub-operators. For the serverless backend, we use two queries as service systems, Athena and BigQuery as baselines. As we observe, Modularis with S3 Select is comparable to BigQuery for the majority of the queries but slower than Athena. The larger running times of calls to S3 Select are because the service returns chunks of uncompressed CSV data through the network. We can improve the performance significantly by using our specialized Parquet scan operator, which reads data in compressed format and also pushes down projections. In that case, Modularis outperforms both baselines in all queries except for query 3, where Athena is marginally faster thanks to a better query plan. For queries 1 and 6, the running time difference is due to the parquet scan operator, which is optimized to push down projections while reading data in compressed format. For the other queries, the specialized lambda exchange operator can run workloads involving data exchange between workers faster than commercial baselines. This is evident because the workers are mostly bounded by network bandwidth and latency. The current performance of S3 Select illustrates the advantage of modularity. Today, we can use the much faster alternative of our optimized parquet scan, but using S3 Select can be easily enabled if AWS improves the performance of their smart storage engine in the future. To conclude, Modularis matches or improves the performance of highly specialized databases, both installed locally and also in the cloud. It can also be easily tailored to new hardware, platforms, and cloud features just by rewriting the new sub-operators and their rewriting passes. We continue evolving Modularis by extending to different than relational workloads, for example machine learning, to more execution platforms, and to incorporating FPGAs as coprocessors. Thank you very much for your time.